Lesson 31, into the matrix. We'll be able to identify different types of matrices so that you know a matrix is a singular term, whereas a matrices is a plural. That's what we refer to as multiple matrices. Really quickly, today's fact. This 31 is the third Mersenne prime. Mersenne prime is when you take 2, you raise it to the power, and you minus 1. So the first Mersenne prime happens to be 3, because if you take 2 to the power of 2, which is 4, minus 1 is 3. The next one, Mersenne prime, 2 to the power of 3 is 8, minus 1 is 7. Then this is the third one, because you might think, well, what about 2 to the power of 4 minus 1? That's 15. 15 is not a prime. The 31 is the third Mersenne prime. Now, what's so special about Mersenne prime? Well, the Mersenne prime, the 50th Mersenne prime, was discovered on January 3rd, 2018. Mersenne primes are known as the largest, there's special kinds of primes. The largest one happens to be 2 to the power of 77,232,970 minus 1. Exactly the same as 2 to the power of 3 minus 1, except that 3 is now huge. They actually get computers to do these kind of searches, and it turns out it's just a computer lab in a laboratory and at a university. At night time, they just get all the computers to do this search for the Mersenne primes. It's kind of neat because, if you win, you get $3,000. You can actually set this up on your own computer. You could actually do this right now, but you would have one computer, whereas they would have something maybe a couple of hundred computers. So it's going to be hard, but it's just a probability. Maybe your computer will find it before they do, and you could get yourself a nice $3,000 for just leaving your computer on at night. So I don't know. The Mersenne primes, they're kind of cool. They have other properties as well, but it's already getting too nerdy here. So I'm going to stop there. So matrices. Where do I go? A matrix is essentially, I'm just gonna talk to you guys about matrices for a second. Matrices are very interesting because matrices are essentially a unique kind of, matrices are like a unique kind of mathematical construct, okay? It's sort of like this. When I talk about something like algebra, I'm building algebra on top of your idea of numbers. When we talk about, sorry, I can't even write here. So we can go from numbers we can go to something like algebra, and that can lead us into more complex things like graphs. And when we talk about, I don't know, something like, we talk about angles, that can then lead to trigonometry. But matrices are like their own little thing. Matrices don't really connect with anything that has come before. The thing about matrices is that they don't connect. The reason that they don't connect is matrices weren't, when I talk about algebra and I talk about angles, I'm talking about algebra was discovered in the 1,000 years before Christ. That was discovered in India by Algebra, and what he did was essentially he took teachings from China and he took teachings from Latin, Rome, and they put them together. And I could talk about angles, which was discovered in ancient Greek. But when I talk about matrices, matrices were invented in 1850. So compared to these guys, which are thousands of years old, matrices are pretty young. They're pretty young and, hip and youthful, right? They're only 100, 106, 70 years old. They're pretty new. And we actually know specifically, again, just like how we know who came up with algebra, we know that an English mathematician known as Sylvester and Cayley, they were the ones that came up with, they were the ones that officially sort of came up with matrices. The reason that matrices are unique when it comes to mathematics is that they don't follow some of the original rules. They don't follow the rules of arithmetic. So a lot of these follow the laws of arithmetic. And there are laws of arithmetic. But these don't. They don't follow the rules. So if I take the idea is, what do you mean they don't follow the rules? Well, the idea is this. If I take 2 times 3, that's the same as 3 times 2. That's a law of arithmetic. It's called the law of, what's it called? I can't remember what the law is. They're both the same. But if I take A times B, and I take B times A in a matrix, they don't have to be the same. They can equal different values. And that's one of the ways that matrices are unique. They're a unique way to add and subtract, multiply, and do maths. They're just completely unique. And it just so happened that matrices would then become a really great way to do things like physics, like computing, like, chemistry. They turned out to have a lot of important uses in things. And so therefore, that's why we sort of teach students what matrices are, because sometimes you might find that they're very useful for a particular case that you're trying to work on. But I think it's also useful to talk about matrices as just like, hey, this is very different to what we've done before. And it's also a really good test. I love matrices, giving year 11 matrices, because it's a good test to see, right, the first topic we did was can you deal with numbers, like, percentages and stuff. You've done that since year 7. The second topic we did was financial maths. You've done that since year 9. The third topic we did was algebra. You've done that since year 8. But matrices, for many of you guys, these are brand new. So it actually gives me an idea, how do you students deal with new topics? That's what I would love to see. So what can we start off by talking about with matrices? A matrix is the plural is matrices, is a regular group of numbers set out in rows and columns. Here is an example of a matrix. It's got rows and columns. The rows run horizontally. The columns run vertically.
Sir,
Yo.
did you say regular or rectangular?
I said rectangular.
Okay, because I heard regular for some reason.
Oh, that's right. Maybe I said, you know what? I'll give you the benefit of the doubt. I probably said regular because I didn't read the word. The advantage of this is you can watch this video later on. You can pause it and write a comment under the YouTube video and say, see, I was right. But yeah, okay. Anyway, they're rectangular groups. So you can't do a matrix in a triangle. You can't do a matrix in a weird L shape. They're set out in columns and rows. Okay, so this is pretty basic here. This is a matrix. Oh, I really, actually, you know what? This is actually not 100% correct. To be honest with you, it's realistically not a group of numbers. It's not pretty much a group of elements. I'm going to say what an element is later on, but like, for example, I can do a matrix like this. That is still a matrix, even though it contains a pronumeral. And you could also do matrices that would look like this. That's also a matrix. So yeah, you know what? Numbers isn't even correct either. This one has the elements are, random. The elements are, in this case, an element. We're going to introduce the word element, but in case if you've probably already figured out, an element is just something that goes in a particular spot in the matrix. In this case, they are the things that go in each spot are actually equations. You can have even more complex equations. What you can't have is this. You can't have this, because that's not allowed. You can't have just an empty spot in a matrix. You just can't do that, because then it's no longer a rectangular matrix. You can put a 0 there. That's okay. You can have negative numbers, put zeros, but you can't just leave it blank. So that's the basics of what a matrix is. Again, rows versus columns. Remember, rows run left to right. If you've got a row in a cinema, that's like running left to right. If you've got a row in a table, it's running left to right. This is all this page is for. Whereas columns, think of columns like columns at the front of buildings, at the front of libraries. They go up and down. These are some examples of some Roman columns that exist around the world, and some of them look quite fancy. But yeah, the idea is it's just up and down. So just make sure you do that, because the amount of little silly mistakes people make because they get columns and rows confused, it's a little bit embarrassing. So make sure you know which one's which. So let's now start to look at this. The numbers in a matrix are called its elements. Okay, you know what? As I said, it shouldn't really be numbers. It should be just the parts. Obviously, we're always going to use, but yeah, again, the numbers is, I guess, what it means. The things in a matrix, in each, call its elements. This matrix here, A, is Aij is the element in row I, column J. Okay, so that's what this means. The first letter is like the row, the second one is the column. And it's very similar to the first one being X and the second one being Y. Remember, X is left and right, and Y is up and down. Doesn't matter how you remember it, but that's sort of thing. Can someone tell me in chat, what is element A21? Using the fact that we know now that how it works. What is element 21? Five? Someone's guessed 5. Okay. Let's try this. Okay. Let's go have a look here. Well, element 21 is going to be in row 2. So row 1, row 2. Right. So it's going to be in this row, and it's element 1. So it's the first one along. Yep. Guess what? It's 5. Good job. So therefore, what's element 1, 2 going to be? Element 1, 2 is going to be 4. Yep. So we go 1, 2, 3. We're going to go 1. We're going to go across 2. It's going to give us 4. Perfect. So this is how we can quickly and easily find different parts in a circuit. In a circuit. Jeez, I've been teaching too much physics. This is how we find different elements in a matrix. Now, in case you don't know, we number things left to right and top to bottom. Very similar to how we would do it in a Western sort of reading a book. You read it from left to right, top to bottom. Same exact way, it's just for a matrix. So this is how we can find a particular part of a matrix. And yeah, as I said, there can be numbers, there can be letters, there can be anything. Let's keep going. So what types of matrices can we get? Well, we can get, and that's pretty much the goal of today's lesson. The goal of today's lesson, by the way, is we will be able to identify different types of matrices. So first type is called a row matrix. Okay, a row matrix, there are lots of different types, but we'll just talk about this one. A row matrix has just one row. That means A11 is the first row, first element, that's 3. A22, that would be the second row, but there isn't a second row. So we just say it doesn't exist. You could write NA if you wanted to, not available, up to you. So that's the first type of matrix you can get. It's called a row matrix. Row matrices, you might think, oh, it's just one row. That doesn't get used often. It actually gets used a lot for some very special reasons. But I don't think we're going to actually talk about them. Yeah, knowing that they're called a row matrix is useful. If we know there's a row matrix, then there's probably a column matrix. And guess what? There is. Column matrix is 3032, the postcode for Braybrook. Let's grab a look at this. Just one column, row 2, element 1, row 2, element 1, that's a 0. Let's look at one more. The last one is called a square matrix. Now, a square matrix has special properties, and we're going to talk about square matrices a lot. The idea that makes a square matrix important is that the number of rows equals the number of columns. You could write that in another way if you wanted to. You could write Aij, we're going to talk about order in a second. But yeah, the idea is the number of rows is the number of columns. So you can have a square, you can have a square matrix like this. You can have a square matrix with like this. The next one's going to be a 3 by 3. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And then, yeah, so on and so forth. You can build them up and make them bigger. This matrix, you can see, hey, look at that. It's got a negative number and it's got a half. I'll put the half in there just again to remind you that you can have, it doesn't have to be whole numbers either. So you can have halves. We could put a square root 3 in there. It doesn't matter. It has to, it just has to be filled with something. So those are 3 major types of matrices. Matrix, row matrix, column matrix, square matrix. The other one's just called rectangular matrix or just a regular matrix. So these are the main types. There are other types as well, but we're not going to go into, like, for example, an identity matrix, a null matrix, but we're not going to go into those until we need to go into those. I think we go into identity matrix about 5E, I think is when we start talking about those. So at the moment, let's just keep it simple. Talk about row, column, square. Next, though, is the order of a matrix. Now, I haven't got anything written down for this slide, so I'm just going to draw. I haven't got any like fancy animations or anything on this slide, so I'm just going to have to work by hand because I think it's because I got a little bit sick of. At this point in time, when making the slides, I think I got a little bit tired of just trying to make matrices all the time. So the order of a matrix, the order of a matrix is the order of a matrix is the dimensions. Is the dimensions of the matrix, which essentially means its length by its width. Well, it's, hold on, let me just make sure I get this right. Yeah, no, what it essentially means is like its length by its width by its length. I guess these things are interchangeable, it doesn't matter. But essentially it's its rows, the number of rows, multiplied by the number of columns. Well, not multiplied, but we're just going to use an X symbol, number of columns. They always use this X symbol, but they don't actually want you to multiply it. They just want you to write the X. Let's do some examples so that this makes a little bit more sense. Let's start off with a matrix. Let's go purple. Let's go for a matrix that looks like this. We're going to go with 10, 11, 24, 16, negative 8, 0. Okay, now this matrix has this matrix has 2 rows and 3 columns. So therefore the order of this matrix is 2 by 3. Okay, and that's how we write down the order of the matrix. We're going to use these orders later on. But at the moment, we just want to show you how to create them. Let's do another example. Let's do one that looks like this. We'll go with 3, 0, 2, 3, 3, 1, 3, 6. Cool. This one has 1, 2, 3, 4 rows, and it has 2 columns. So this is a 4 by 2 matrix. So a 4 by 2 and a 3 by 2. So that's just the different ways we can, and you could have a 3 by 2. So even you could have a 2 by 3 and a 3 by 2, and they would look completely different. In fact, let's go have a look at these ones back here. This one here has 1 row and it has 4 columns. So it's a 1 by 4. But this one has 4 rows and 1 column. So it's a 4 by 1. This one has 2 rows by 2 columns. So that means, and you will find that when these two numbers are the same, then that means they are square. And because again, those two numbers essentially mean that the first column and the number of columns and the number of rows are the same. Now, what I'm going to do now is, so are there any questions? I'm going to give you guys a second here. I'm going to open up chat. Are there any questions about what the order of a matrix is? Like any queries? No, we're all good. So this is just the basics mostly for this first two. The first two exercises are just the basics. Okay. This is sometimes, I should point this out, the order of a matrix, just because I wanted to double check before I made a mistake, is sometimes referred to as the size of a matrix. So sometimes, so if we could talk about the size of this matrix is a 2 by 3. That's how another way that you can refer to these values is the size of the matrix. But order and size are the same sort of thing. I guess I just didn't want to start with the word size, so I didn't want you guys to think of that. And no, you don't have to multiply them in order to get the order. Let's now look at, I want to show you guys a practical example for 2 reasons. One, because once I show you this practical example, you guys can actually do all the questions in 5A and 5B. And 2, because it's also, the stuff that I talked to you guys about so far is pretty basic. Let's talk about this here. So there are lots of ways that you could do practical work with matrices. And one of the great ways that we love to do practical work with matrices is we've got this thing in maths called graph theory. Now, when we talk about graph theory, we're talking about pictures. And we've got these things called networks. And networks and graphs are great, but ultimately they are pictures. And sometimes in maths, we want to turn a picture into the raw data, the raw information. And so we need a way to be able to do that. And a matrix is a great way to do that. In this example below, 4 towns are connected by rows, as shown in the figure and this figure below. This information can be represented as a matrix. Let's talk about how we could represent this information as a matrix. Well, we've got 4 rows right now. Let's look at this different town. Like if these are towns, yeah. Let's look at town. C looks a pretty good town to live in. Because C, you can go to A, you can go to D. You know, C looks like a pretty popular place to live. B, on the other hand, looks like it's, not a great place to live because you can only get to two towns, A and D, and there's only one way to get to them. So if, if a tree falls onto the road and, blocks your car, guess what? You're going to have a difficult time trying to get to, you're going to have a difficult time trying to get to A. You're going to have to go through D, through C to get to A. So that's just, want to do that for basic reasons. I want you guys to look at this picture and go, oh yeah, I can see that. I can sort of see what's going on here. I want you guys to sort of imagine this is a map. If I lived in town C, the other advantage is there's lots of routes that I can go down to get to D. I could take the scenic route that goes past, that goes over the mountain, and you can see some waterfalls. I could go via the beach, maybe instead, or I could just take the straight route through the forest. Okay, I'm making stuff up. Hopefully you guys get that. But the point I'm trying to say is look at this as an actual map, not as a random maths concept. So let's say that I draw this matrix here. I'm going to do this part bit by bit. Let's say that I want to go from, A. Okay. How many ways are there to go from A to town C? Can you guys tell me how many ways are there to go from town A? How many ways are there to go from town A to town C? Can someone tell me how many ways are there that I can drive? If I was like trying to plan out a road trip, how many possible ways could I have? 2. Thank you, Logan. 2 is the correct answer. Whoa, I accidentally blew that. Okay, cool. All right, so we've got 2 ways. What about if I wanted to go to B? How many ways could I go to get to B? How many roads are there that go from A to B? 1. There's only one way I can go from A to B. That's this one little road at the top here. How many roads are there that go from A to D? How many roads are there that go from A to D? And when I'm talking about roads that go to A to D, I'm talking about roads that go straight from A to D. 0. Perfect. There are 0 roads that go from A to D. And are there any roads that go from A to A? Are there any roads that start at A and then end up back at A? Like round trip roads? Because what do you guys think? Are there any roads that start at A and then loop around and finish at A? Yes or no? No, there's not. There are 0 ways for you to take a road from leaving A and coming back to A. So what we've done is we've now converted all the roads from A into a matrix. There are 0 ways to get from A to A. There are 1 way to get from A to B. There's 2 ways to get from A to C, and there are no ways to get from A to D. Let's keep going. I mean, sorry, does everyone get that? Does that make sense how I created this from town A, how to get to these individual road places? Does that make sense? Does anyone want me to go back over it? I'm going to assume by your silence either everyone's okay with this or, yeah, at the moment, no, well, here's the thing, right? Baden, you're on the right track. It's not a 1x4 though, right? Because what about town B? How many ways are there to go from B to A? Well, there is 1 way. How many ways is there to go from B to B? Well, there are no ways to go from B to B. There's just no circular tracks. How many ways is there to go from B to C? Well, from A to C, there were two ways, but from B to C, there is no way to go from B to C. How many ways are there to go from B to D? Well, guess what? There's one road, so we got one road. Now, C. Can I get someone in chat to write down what numbers should I be writing here? What numbers? You can write down in chat something like this. 3, 4, 5, 6, whatever it is. Can someone write down what are the numbers? How many ways are there to go from C to A, C to B, C to D, C, and C to D? What are those numbers going to be? 2003 is what we've got from let's see. We've got two ways to get to A. We've got no way. Got no way to get to B. We've got no way to get to C. We've got three ways to get to D. Yep, I would agree with 2003. And so the last one is D. D is the last one here. How many ways are there to go from D to D? Well, let's look at this. How many ways are there to go from D to D? Well, it turns out that there are. From D to all the other letters. Let's look at this. How many ways are there to go from D to A? None. How many ways are there to go from D to B? One. How many ways are there to go from D to C? 1, 2, 3. 3. How many ways are there to go from D to D? 0. That makes us a matrix which is 4 by 4. It's a square matrix. And it includes every possible root and how many there are. And that's why matrices are really good here. We don't need to think about how many possible roots there are because we can write them down. Now, what's useful about these is that we can add values together and we can, what's useful about it? If you add these, what that'll tell you is that'll tell you how many roads to A. And you notice, by the way, I'm not sure if you guys can see, but there's almost a symmetry. 0, 1, 2, 0, 0, 1, 2, 0, 1, 0, 0, 1, 1, 0, 0, 1. I'm not sure if you can see my cursor. 1, 0, 0, 1. 2, 0, 0, 3, 2, 0, 0, 3. And then we've got 0, 1, 3, 0, 0, 1, 3, 0. So if you add all of these values, they'll tell you how many roads out of A. So let's look at this, check to see if it works. 1 plus 2 is 3. There are 3 roads out of A, and there are 1, 2, 3 roads out of A. Great, cool. And I can look at any of these. I can look at C. We can say, well, there is 5 roads out of C. Let's count them. 1, 2, 3, 4, 5. There are 5 roads out of C. So that's how you can create you can convert a network to a matrix. Now, let's do one more example here. The last example I've got for you today is this one here. We're going to draw a map of this network. So we're actually going to go backwards this time. So this time, how do you go backwards? Well, how I would go backwards is I would do this. I'd say, well, we're going to do, well, oh, look at that. The steps popped up for me. We're going to draw 3 points. We're going to call these points A, B, C. Now what we're going to do is we're going to join A to B, B to and C, and we're going to work out how they go. I'm going to split the graph in half. I'm going to show you what that means in a second. I'm going to address each connection and cross it off. I'm actually going to do these in different colors. So I might use blue and green. Let's go. This is A, B, C. This is from A, B, and C. And this in blue is to A, B, and C. I'm going to cross them off as we go. So let's start with the first one, A to A. There are no roads that start at A and go back to A. There are no roads like this. You can have roads like that. I want to point out you can have loops. But in this case, there are no loops from A to A. Cross that off. What about from A to B? There are two roads from A to B. So let's draw two roads in. Here's one road. Here's another road. There are two roads from A to B. Now, we can actually double up here. If we know that there are two roads from A to, well, you know what? I'm not going to double up. I'm just going to do this step by step. We know there is one road from A to C. So I'm going to draw that one road from A to C. Let's draw that in. One road from A to C. And we're going to cross that off. All right. We're done. Let's move on to the next one. Now, from B, there are two roads from B to A, but I've already drawn two roads in from B to A. I'm actually finished that already, so I don't need to add anything new. I know there are 0 roads from B to B, so there's no roads connecting B to B. And I know there are 3 roads connecting B to C. Now, I haven't got 3 roads drawn in, so I'm going to have to draw them in. There's 1, 2, 3. 3 roads connecting B to C. Okay, cool. So I'm going to cross that off. Done. Next one. From C to A. Okay, well, I've already got the one road from C to A. Done. From C to B, I've already got the 3 roads connecting C to B, so I don't need to draw them. And from C to C, well, there are no roads connecting C to C, so I don't need to draw them. This is our map. Now, what I mean by splitting the graph in half, to be honest with you, you don't actually need to split anything in half. I'm actually going to remove this idea from it. The idea is that sometimes you will find that some of these roads have already been drawn in for you, so you don't need to draw them in. So we have to address each connection, but we don't necessarily need to draw each connection here, because the idea is there is symmetry. The road from B to A, there are 2 roads from B to A because there are 2 roads from A to B. Those 2 things are symmetric. And there are 3 roads from B to C because there are 3 roads from C to B. Those things are symmetric. There is actually a line of symmetry through the middle of this matrix. But we don't really care about that. It's not too important. Ladies and gents, believe it or not, that's it for all that I wanted to talk to you guys about with matrices.